We're going to look at dynamically allocated array as well as the static array. We talked about this. Let's consider the following code where you have a char pointer. This char pointer points to this newly allocated memory of 3 bytes. Each char is 8 bytes. So you have 3 elements here, P0, P1, and P2. When you're using the bracket notations here, you print out the value of whatever is inside this array. P itself is a pointer, but P also points to the very first element or the allocated space for this array of 3 characters. You have this dynamically allocated array that requires a corresponding delete. At some point in your code to delete this pointer, if you don't, you're going to run into memory leak, which is not good. If you just do a new char 3, so goes into your heap memory and allocate 3 bytes of memory spaces there, respectively, F10, F11, F12, right? For the illustrative purposes, we use F10, 11, 12 to indicate the hexadecimal. 0 times, FA10. 10, 11, and 12, and P points to the very first element address. So this is what we called allocated array. This entire array lifetime must be managed by your code. Delete bracket is used to manage their scope. So that's what this dynamically allocated array looks like. Let's move on to the statically allocated array and see what the differences are. We have dynamically allocated example. We use a integer size to indicate the amount of memory that we need. The compilation sets aside the amount of space needed for this declared pointer. It also dynamically allocates char size, which is array of 3 chars stored inside your heap memory. Then we also have statically allocated. By statically allocated, this is what we call declared allocated. So this declared allocation looks like this, where you have integer size and then you say char p. This entire thing is actually compiled, and also memory is allocated on the stack at compile time. The difference between the two is one of them takes care inside your heap and the other one in the stack memory. This dynamically sized or allocated code, it's a pointer. This statically declared array decays to a pointer at runtime, actually. Sometimes you see something like this, where people would just create a non-constant size and then do this. Before C++11, C++11 is the standard. This used to crash, but then C++11 onwards, this gives you some sort of compiler warning, and it says something to the effect of the size of an array must be a constant expression. Starting C++11, the compiler expects something like this. So T is generic and D is the declared type. You have some sort of constant size. This is the constant expression size. In order for this to work, without this warning, is you have to declare this size to be const. This is necessary because this is not like your dynamic allocations where pointer or allocated memory lifetime is managed by your system. With a declared array, the size must be coded into the type so that the constructor, right, knows what to do. The size of it must be a constant. Let's move on to the next page. Let's go back to the dynamic allocations, and this will tie into what we call pointer arithmetics. Knowing that P refers to the very first element of the array, we can dereference P. It'll get you the value pointed to by the very first element, which is 0 index. And the value of that would be P bracket 0. This and this are the same. This is where the next chapter comes into play, where we talked about pointer arithmetics with regard to pointer arithmetics. If you add 1 to a pointer, what it does is simply advances to the very next locations adjacent to P0. So the very next location is at F11. When P gets advanced to the very next memory location, when you dereference it, you get P1. You can't just write extras P plus 1, because what happens is extras P, this dereference takes precedence over the addition sign. So what you need to do is make sure you have parentheses. And let's just say if you want to go over by 2, this will give you this one too. In C++, there is no array bound checking. If you just arbitrarily add P plus some n, and this n exceeds the boundary of your array, and try to dereference it, you could be running into what we call segmentation fault. an error will pop up at runtime saying that you're running into some restricted memory locations where you're not supposed to be. Let's illustrate dynamic memory allocations of an array. Let's just say this integer p start, which is a pointer, equals to new. There are three integers, and we're going to initialize it with a value of 8, 9, and 10. This means that there is a integer array with three elements. They have values 8, 9, and 10. P is the pointer, right? So if you print out a p, is going to give us the memory address of that 8. You can use pointer arithmetic. You can advance p to the very next memory location. This means the next allocated memory location. So since we got three of them, we can keep going like this. Be careful since we only got three elements here. So let's say do p plus 10. If this p plus 10 memory location is being used, you're going to get segmentation fault. And that's not good. Do not do p plus 10, go outside of your bounds, because C++ would let you do that. The compiler is not going to bark, but you're accessing restricted memory areas that you don't want to. You can simply dereference p. P points to the very first one. You get 8 coming out of it. Let's double check. And indeed, we get 8. If you want to get 10, 10 is actually 2 memories over. You have p pointer arithmetic plus 2 to reference the entire thing. And make sure that you have this entire thing, right, in the parentheses. And that will actually give you 10.